All right. So last class we had done up to virtual circuit switching, and we could see that how VC switching actually works. Okay. So as a summary, I would like to say that it is basically a kind of switching technique where the source to destination path behaves kind of like a telephone circuit. Okay. So how does it work out? So we have a call setup phase, we have a communication phase or data transfer phase, and then finally we have a tear down phase. So in the call setup phase, basically the VCIDs are exchanged and the path is known. So the resource is basically getting reserved. And then after that, once the VCIDs are updated in the forwarding tables, then the data flow will happen. Once the data flow is done, then the tear down phase starts and it is initiated from the source's side. Once the source gets to know that yes, all the data that it wants to transfer has been transferred, so it will start the tear down phase, and then the destination will be informed that the tear down phase has been initiated. So the destination will also send an acknowledgement, and with that all the forwarding tables which are intermediate in between the two nodes, they will update their tables. Okay. So what happens in this case? Every packet is basically identified using a virtual circuit identifier and not the destination host ID, which basically reduces the time for reading the host ID, right? So makes it more efficient. And since the forwarding tables keep the information of this VCID of the different links in between the source and destination. Therefore, we say that every router between this source and destination path maintains state for each passing connection. Okay. So, of course, just because we know the path and we are basically saying that this is the VCID, we say here that the link router resources are basically allocated to the virtual circuit. So this is basically over a packet switched network, we are virtually creating a circuit switching path. All right, so this is about VC switching. Now, I had stopped at this and I wanted to tell you in the last class itself that there are two types of VC switching. Okay, one is where the network administrator configures the state. It is kind of a permanent circuit, right? So that's what it is called. That is a permanent virtual circuit where the network administrator will configure the state. And there is a switched virtual circuit, which is basically an on-demand circuit. Okay, so it is what we have already studied by now, the switched virtual circuit. That means we will have a setup phase, we will have a tear down phase, and the data communication will happen in between. Okay, so these are the two types of states that we have. So let's talk about the states a little bit. So PVCs or the permanent virtual circuits. So they are administratively configured. So how is it configured? Basically by manually by the network administrator. Okay, how does he do that? By finding out that what should be the dedicated signaling protocol, or by piggybacking the information on the different routing protocols. Okay, so this is configured administratively, and because it is a permanent one, so therefore it will definitely last for a long time. Okay, but the problem is that see, if you have a very large network, okay, so and on that network you want to set up a permanent virtual circuit, then it will become overwhelming for the network administrator himself, right? So that is a drawback that we have when we are using PVCs. Uh, was there any network issue when I was talking? Did I miss some parts, or did anybody miss what I was talking about?
No, ma'am.
Okay, okay. Please let me know, okay, if there is some network issue, if you are unable to hear me out or something. Okay. So now let's get to the switched virtual circuit or SVCs. Okay, so it is definitely a dynamic VC. So because it is done on demand or basically per call basis. So we have already seen how a virtual circuit is basically set up, a non-permanent virtual circuit. That means if there is a request, then there will be a setup phase, then there will be a data communication, and after that there will be a tear down phase. So I will not get into this, you know, entire steps once again because we have done it in the last class itself. So let me just get to the summary of SVC. See, what happens in SVC? So whenever the call setup phase is initiated, the source will send the VCID information towards the destination, just to acknowledge to the destination that I am trying to set up a VC circuit. Then once the destination is ready to have the communication, the destination will send an acknowledgement. With that, it will send the VCIDs and also will know that okay, this is the path that is being followed. Okay, so with that, the path is also being known, the VCIDs are also being shared, and then both the source and the destination are basically connected virtually using a VC circuit. So there are two communications that are happening between the source and the destination. Okay, so this setup that takes a full RTT or round trip time. Okay, so this is very important in SVC. When we are trying to set up, for every SVC you will take one RTT at the setup phase. Okay, so that is one important point. The next is that buffers will be allocated in the switches as the connection is set up, right? Otherwise, how will you keep those information that you are basically trying to send to the next link, right? So buffers are allocated in the switches as the connection is set up. Then advanced sliding windows are kept. Then we also have the circuit setup requests, which may be rejected if a node does not have enough buffers. All right. So suppose there is, see, this is a packet switched network basically, but you are trying to have a circuit switch on top of it. All right. So there will be buffers for switches for keeping those requests until everything or until the resources are available, and then it can actually set up the path, right? That is why we are having buffers at the switches. Now if the buffers are not available, if there are not enough, if there is not enough space in the buffers in the intermediate switches, then of course the requests will be rejected. Okay, so that is what this fourth point is basically talking about, that circuit setup requests are rejected if a node does not have enough buffers. Okay, and of course we will have hop by hop control here, right? Link to link, right? So that is what SVC, so these are basically the properties of SVC that we have. So let me just tell you that what is the delay that is incurred in a virtual circuit network, whether it is PVC or whether it is SVC. For SVC, every time you will have this setup cost with you and tear down cost with you. But when it comes to PVC, because it is more of a permanent nature, this will happen only once. You will only have this transmission time for you. Okay, so let's see how is the total delay coming out. So you have one RTT for the setup, as I already mentioned. So full one RTT for the setup. Then you have the transmission time, and then finally once the transmission is done, then you have the tear down phase. Okay, so this is the entire delay that you have in a virtual circuit. Okay, so where do we use virtual circuits? So this is a concept, right? Where do we use it? What are the use cases? So there are two use
Excuse me,
cases.
ma'am.
Yes.
Ma'am, you told that it's a packet switch network, right?
Hmm.
So in packet switch network, we have queuing delay. So do we have queuing delay in this network also?
We would have no. I also told that if there is not much space in the buffers, then those packets will be dropped. Right? There are
Okay,
buffers in
ma'am.
the switches. I told na. So there will be.
Yes,
Okay. Okay.
ma'am. If buffers are full, then the packet will choose different path, right, to towards destination.
No, if buffer is full, the packet will first get dropped. Then you again send a request. Then you will try to find another path.
Okay,
If
okay,
buffer
ma'am.
is full, if there is no space in the switch itself, no?
Yes, ma'am.
Huh. Okay, let's
Okay.
get to the next part then. Okay, so there are two basic applications for which in which we use virtual circuits. One is ATM and another is MPLS. Okay, I think MPLS, third year BTech students, I have finished MPLS in computer networks course, I remember. This one I will still go through MPLS for all others a little bit, but I will focus more on ATMs right now. Okay, it is a very important concept, so please pay attention on ATMs. So what is ATM? Let me start with the full form. It is known as asynchronous transfer mode. Okay, so what is it? What is ATM? So, we are always thinking of using both the goodness of packet switching and the goodness of circuit switching. With that concept, the virtual circuit concept came into picture. Okay, so this ATM was basically designed so that we can create a network, or we can have a network that can handle both the high throughput data traffic, and also it can handle real time low latency content. So it can also it can handle basically voice, video, and all other types of high throughput data traffic also. Okay, so that is why ATM was basically considered. Now, let me tell you, ATM is something that we use in the backbone networks. Okay, this is used in the backbone networks, and it somehow uses the concept of telephone networks as well as our data networks, our usual data networks. So we have already read about data networks in our computer networks course. Telephone network, we have some idea from circuit switching, right? We will read about telephone networks at the end of this module, because it uses concepts of all of these a little bit. So let's not get into telephone network right now, but it does take the best of both worlds, or tries to take the best of both worlds. Okay, so basically in telephone network you have a dedicated connection, whereas in data networking you do not have that dedicated connection most of the times, but you can make use of the resources more efficiently if you're using the concepts that we use in data networking, right? So this is the basic concept of ATM. Now, why we are using ATM? So there are two important points. So as I told you, that it tries to use the best of both worlds. So telephone networks, basically because they are using a dedicated connection, they support a single QoS, but they are having an expensive setup cost. Okay, so that is one point. Next is that suppose we do not use telephone networks, but we are trying to check or trying to use packet switch networks, then they do not guarantee any QoS. It's wrong to say that it does not support QoS. Packet switch networks actually do not guarantee any QoS. Okay, but they are flexible and they are having very cheap setup cost. They are simple also, right? So ATM basically wants to use the best of both. So what it does is it provides a given QoS, okay, and it is also having a cheap setup. Okay, so this is the reason why ATM is preferred. Now, some of the features of ATM are as given here. So too many points are here. I'll just go through the points a little bit. Some of the main points basically. So ATM is a connection oriented circuit, right? Because it is using virtual circuits. See, it is not exactly connection oriented, but we are using virtual circuits. So we say that it is connection oriented in nature. Okay, so what is one more feature? So see, it is using both the qualities of packet switched and circuit switched network, right? So what it does, it transmits information in fixed size packets. Okay, in packet switched network you can have variable size packets, but here what it is doing is it is dividing the data into small chunks. Those chunks are known as cells, but these cells have a fixed size. Okay, what is that size? That size is basically 53 bytes, 48 byte payload plus 5 header. Okay, that is the size of the cell. Now why are we using fixed size packets here or cells? Because one, if you use a fixed size cell, it will make the switch designer's job easier. Okay, and of course, you know, at the end of the day, when you also have a fixed size packet, it will make it scalable to high speed. Okay, how? Because the lookup in the table becomes much easier when you have a fixed size cell. Okay, so that is the reason why we are using fixed size cells. Now, one more feature that we have here is that it uses asynchronous TDM. Okay, that means all the cells are transmitted asynchronously. Then that means what? That is, cells can be transmitted in any order, and ATMs can carry multiple types of traffic. Okay, because that is what we actually want. We want that we can support high throughput traffic also, and we can also support traffic which is basically constrained using delay or some real-time traffic. Okay, so it can basically support many different types of traffic. However, the delivery of the packets are not guaranteed, and it uses statistical multiplexing. I will explain what is statistical multiplexing. Please remind me in the next class. I will probably show you a figure for statistical multiplexing. Okay. Um, I think, do you guys have some idea of what is statistical multiplexing from your digital courses? Did, I would just, yeah, any idea of statistical multiplexing from your previous core courses?
No.
No idea. Okay, fine. So I will just show you how it works out. Okay, today I do not have my tab with me. Otherwise, I will draw and show it to you. Tomorrow's class, I will show it to you. Okay. Then we have, of course, it has having an independent. It is independent of the transmission medium. Okay. Now let's see how ATM will work, but before that, what are the proposed use cases for ATM? As I already told you, it provides connectivity in the backbone network. Okay, so the one of the proposed most important proposed use cases for ATM is that it provides connectivity in internet backbones, and it helps in aggregating residential broadband networks such as cable, DSL, ISD, and etc. So in that also in the backbone, the ATM can work. It can provide as a carrier infrastructure from telephone and private line networks, and it can also provide variable rates for telephone network backbone circuits. Okay, so these are a few use cases that we have for ATM. Now let's get to the ATM reference model. So see, ATM has different layers. Okay, so we do have a reference model for ATM, which basically or approximately maps to the three lowest layers of our OSI model, or the TCP/IP model that we have already studied in our networks course. Okay. Now think about it, why it is only 3 layers. I will again come to this point in the next slide probably. Let me first start with the reference model. Okay, so the ATM reference model is basically divided into 4 planes. Now please do not get confused here with this ATM adaptation layer, ATM layer, physical layer, etc. in this diagram. In the above one, so these are basically the layers, and these are basically planes, the ones which are written as plane management, layer management, control plane, user plane. These are the 4 planes. Okay, so what basically is the task of these planes? So control plane is having all the functionalities that are responsible for generating and managing signaling request. That is any kind of connection management. Whatever tasks are there, those are managed by the control plane functionalities. User plane functionalities, they deal with data transport, flow control, error correction, and other user functions. Okay, as the name suggests. And then we have layer management. So what happens in layer management? It basically has layer specific functions. Okay, for example, detecting failures, that if there has been a failure in the connection or not, and if there is an issue with setting up the, whatever the protocol is saying, whether setting up the connection according to that protocol is causing any failure or not. Okay, so these are the tasks of layer management. So this goes on for all the layers. Okay, and then we have plane management. And plane management again, it manages and coordinates functions related to the complete system, hence again works throughout the entire set of layers that we are having. Okay, now there are a few more things that you can see here. I will talk about these are known as sub layers. I will talk about these in the next slides. So let us first see, this is the reference model. Now we are going to talk about the actual ATM layers. Okay, so what did I tell you earlier? That ATM layers basically map to the 3 lowest layers of the OSI or TCP/IP layer. Okay, so what are these layers? Physical, data link, and network layer. Okay, so whatever layers we are talking about, whatever layers of ATM we are talking about right now, they are basically going to map to the tasks that the 5 data link and network layer of your TCP/IP or OSI model will do. Okay, so what are these 3 layers? We have the first one, that is ATM adaptation layer or AAL, and then we have the ATM layer, and finally we have the physical layer. Okay, no change in that name. Okay, so how does it work? We have the ATM endpoints and then the ATM switch, and then we have these layers. Okay, of course this is the physical medium. All right, so this is how it is working. So since it is basically a backbone network, so having only these 3, I mean, since mostly it is used in the backbones, it can also be used in the um, other use cases, as I already mentioned. But if it is being used in the backbone network, then of course these layers make sense. So then we have, the physical medium, and then the endpoints, and then we have the switch in between, which has only 2 layers. Now this, why it is having 2 layers, why it is having 3 layers, please go back to your computer networks course and you will know that why this is like this. Okay, so this is how the protocol layers will look like with different or different hosts with your physical medium. Now what are these layers going to do? Okay, so first let us start with the ATM adaptation layer or the AAL layer. Okay, so what is it mapping to? It is going to map to basically the network layer functionalities. Okay, but But what are these functionalities? So first, it will enable the ATM to accept any type of payload, because we want to in ATM we basically want to support different types of traffic, right? So it enables ATM to accept any type of payload, both either it is data frames in the form of data frames or in the form of stream of bits. Okay, so this is one feature. Then the second is that of course what is the task after that? Because in ATM you can receive it, you can receive the data in the form of either data frames or stream of bits. But within ATM, what do we know? The transmission has to happen via cells, right? So whatever data has been received, that has to be divided into cells, and we know what is the size of the cell already. It is a fixed size cell. So fragmenting them into small and fixed size cells, that is another task. Once these cells are transmitted, then again at the endpoint, as we already know in case of networks or computer networks, in TCP IP also we had studied that, you know, once the packets are received, then you have to reassemble them or basically order them. Okay, so same is here, that is reassembling of cells, that is also the task of this layer. Now there are a few more tasks, and those are divided again into sub layers. Okay, so these are two sub layers that we have. One is convergence sub layer and another is segmentation and reassembly sub layer, which is known as SAR. Okay, so what is the basic task? Why do we need these sub layers? For mapping apps or different applications to the ATM cells. Okay, how is it done? So convergence sublayer basically prepares data to ensure their integrity, providing standard interface. It also helps to offer different kinds of services to different applications. So basically, when there are different applications and there are different cells, first you need to map them, and then with the help of these sublayers, basically you are able to do that. And the convergence sublayer is ensuring that there is integrity, and it provides the standard interface for that, and it also helps that, you know, different kinds of services are provided to different types of applications. So that is the task of the convergence sublayer. And then of course, as the name suggests, segmentation and reassembly sublayer, it basically segments the payload into cells, and at the destination reassembles them, creating the original data or original payload, right? So that is the task of these two sublayers, and it ends the different types of tasks that AAL does. Okay, now let's get to the next layer, which is known as the ATM layer. It also has its different sublayers, but let's first talk about what it corresponds to. It corresponds to the data link layer of our OSI or TCP/IP model. Okay, so it does the tasks of, you know, what basically will be done in the data link layer. So let us see what are the different tasks that it does. It defines the cell layout, defines the header, finds out, you know, what is the routing that is being used. um, it is responsible for the two phases, that is establishment of the connection of the VC, and also tear down, that is release the VC. This is also done here. Then we have switching, multiplexing, and of course congestion control. Okay, so these are the tasks that ATM layer does. Now it has two sublayers in which its functionalities are defined. So physical medium dependent sublayer. So it has this PMD or physical medium dependent sublayer has two functions. One is it synchronizes the transmission and reception by sending and receiving a continuous flow of bits with associated timing information, and also specifies the physical media for the physical medium used. That is, you know, what is the kind of physical medium that is being used, whether it is what kind of cable it is, what is the connector type. So like that, this information is stored by this physical medium dependent sublayer. Now when it comes to the transmission convergence or TC sublayer, it has 4 functions. One is that cell delineation and generating cell boundaries. That is where you will break the data to create that cell. Okay, so that is the first function. Then the other one is that header error control or HEC, which is nothing but it helps in sequence generation and then finally verification at the end. Third one is that it helps in cell rate decoupling, maintaining synchronization, and inserting or suppressing idle ATM cells to rate of valid ATM cells to the payload capacity of transmission system. And the fourth one is that it helps in transmission frame adaptation, packaging cells into frame which are acceptable to the particular physical layer implementation. So we have different types of physical layer implementations, no, which will be told by the PMD as we just saw. So TC, what it will do is that it will help in adapting the cells according to whatever physical layer implementation is there. Okay, so this is the task. All right. Now, next part. So we were talking about this, right? That ATM wants to support different types of functionalities. Okay, so there are 4 different versions of AL. That is the first ATM adaptation layer. Okay, why? Because as I told that we want to give out different versions. Okay, so there are 4 versions here as we can see. AL1, which supports constant bitrate service. I will tell you what is constant bitrate service. What it is a connection oriented strict timing relationship between source and a destination. So constant bitrate service basically provides a connection oriented service, and you get, you know, a fixed bitrate at the end at the destination side. So there can be applications which would probably want that, you know, that I should get at most this much of, or I should get a continuous flow of this much of data rate. Okay, so those kinds of applications can be supported via AL1. All right, then we have variable bitrate services. Like us, we users, you know, we are like, okay, if I'm paying for some amount of money to my particular ISP, the ISP will say that we can provide you up to X Mbps. Okay, they may never provide you up to X Mbps. They will provide less than X Mbps, but they will say that we will provide up to this much Mbps. So this Mbps that you are receiving is actually going to vary. Those kind of services are known as variable bitrate services. Okay, now again it depends that what is the kind of application or what kind of priority user are you. Okay, so if you still say that I want a variable bitrate service, but still I want that guarantee in the delivery of my data, or I want that you know, yeah, anyways, so I want that guarantee in the delivery of that data. So that means I should have a connection oriented network, right? So AL2 is what that AL2 is that version of ATM, or sorry, of AL, that provides variable bitrate service, which is basically connection oriented and can provide strict timing relationship. That means it can be used for voice, video, or even fax. Okay, so this is what AL2 provides. Then we have another version, that is AL3/4. Okay, why it is given like this? Because it supports both CBR and VBR service. Okay, so that means it can support both connection oriented as well as connection less data services. And then we have AL5, which basically assumes that all the cells belonging to a single message travel sequentially, and that control functions are included in the layers of the sending functions. So basically it provides connectionless VBR service. Okay, so these are the 4 versions of AL. Now there are four classes of services that ATM provides, given that you have different versions of AL, right? What are these four classes? See, these are the four classes. Constant bitrate services, that is CBR. I've already told you what is CBR. So CBR is basically used by those connections that require a static amount of bandwidth, which is continuously available during the connection time. Okay, so suppose you are basically a company owner or something, and you want a very high and you are a high priority user for the ISP, so you want a very stringent, or you have a very stringent requirement of your bandwidth. So you pay the ISP, and the ISP tells you that okay, I will give you this amount of bandwidth every time. Okay, as long as your connection is up, you will get x mbps of data rate always. Okay, so that is the kind of network which we call as sorry, connection that we call as CBR, and this is one part or one type of service of ATM. Okay, so there are different types of applications also which need CBR. For example, telephone traffic. Okay, then video conferencing, interactive audio, TV, etc. Some of these applications. So these are some applications which may require constant bitrate traffic. Okay, then we have our rate non-real-time variable bitrate. So that is NRT VBR. Okay, so what is it? Okay, so see, in earlier times, in earlier books, if you find out now for ATMs, so these will be given as class A, class B, class C, and class D kind of services. Okay, but here we are talking about this in the names itself, in terms of their names itself. So this rate non-real-time variable bitrate service, it allows users to send traffic at a rate that varies with time depending on the availability of user information. Okay, for example, emails. All right, then we have rate real-time variable bitrate traffic. Okay, so earlier was non-real time, so you could send it at any time, or you could just, I mean, there's no restriction that, or timing restriction basically. And then we have the real-time variable rate traffic, so where we do have a restriction on the timing. So therefore it is intended for those applications which require tightly constrained delay, and therefore there can be some delay variations also. So some of the applications are that, voice with speech activity detection and interactive compressed video. So these are some of the examples here for RTVBR. Then we have available bitrate or ABR. So what it does, it provides rate-based flow control. Now, depending on the state of the congestion in the network, the source basically controls the rate. Okay, this is obvious for any network in general. Okay, but since we are talking about but in the other ones we were talking either it is connection oriented or something, so then in that case the source need not do this per se, but now because the source is basically in this available bitrate, we basically mean that okay, whatever is available you basically try to use that. So that is why it provides rate based flow control, and the congestion is controlled by the sources side. Okay, so what does the user need to do? The user allows the users to declare a minimum cell rate guaranteed to the connection by the network. Okay, and it is aimed at the data traffic at different types of applications such as file transfer, email. So you are not basically guaranteeing the timing here also. Okay, so whatever is available with you, you are trying to use that. So these are the kinds of applications that can be supported by ABR. Then there is the last one, that is UBR or unspecified bitrate. Again, this is also focused at non-real-time applications, but those kind of applications which do not require any delay guarantees. Okay, so this is used today mostly for TCP/IP. All right, So we are not giving any delay guarantees for these kind of connections. All right. So this is what our ABR is. Sorry, our UBR is. Now we have ATM virtual connection here. So we have what we have already studied. ATM makes use of virtual circuits. Okay, and it also provides a connection between the source and the destination, right? We are basically finding a path, virtual path between the source and the destination, and we are using VCIs. Okay, so there are basically three important points here to note when we are looking at ATM virtual connection. We have the transmission path, that is the actual physical connection between the two endpoints. Okay, it can be between your host and a switch, or between two switches if it is an intermediate, if it is intermediate between the nodes. Okay, so this is one important information that you will require. Another is the virtual path, that is you need the connection right between the two switches. Okay, what is the path that you are basically trying to use? So virtual path will provide a connection or a set of connections between the two switches. And how it is represented? It is represented using a pair. As you can see here, you have the path ID and you have the circuit ID with you. Okay, so this is how the virtual connection is represented in case of ATMs. Then finally you have the virtual circuits. We already know how a virtual circuit is basically set up, and from the virtual circuits we will get that what is the VCI, and that VCI will basically form a particular virtual connection. So you can have a single path with different VCIs for different links, right? So this is how, so with this tuple, you can actually represent that what is the path that the communication will have to follow. All right. So this virtual circuit must be set up across the ATM network prior to any data transfer. Of course, it needs to be set up because we know that virtual circuit we need to set up first. Then there will be data transmission, and after that there will be the tear down phase. Okay. So this is how the ATM virtual connection basically works. And with the help of this, we can support different types of data traffic, and it is mostly used in the backbone network as well as a few more use cases. It mimics or uses the best of both the telephone network as well as the packet switch networks. Okay, so I will not go through the advantages and disadvantages right now. I do have them with me, but I want you to study these. Okay, I have told you about ATM, how it works. So please find out what are the advantages and disadvantages for ATM. Now tomorrow's class, I will try to, so tomorrow unfortunately, I will have the class from 9 to 10 itself. But from the next week onwards, we will have the class according to whatever, decision all of you together take. Okay, regarding the timing. So give me the timing by tomorrow